Thank you, Werner. Thank you for having me. So, I'm going to talk about a challenge which we have at ASML, and it's about balancing between short speed and long-term speed. First of all, who am I? I'm a Dutch guy. I did start my career at Philips as a software engineer, so I did software development myself for 15 years. Then I moved into a line management position, which I continued at NXP, at Bosch, and 2 years ago I joined ASML as a software quality manager. In 2020, I wrote a book. I wrote a book about software quality because I had the vision that software quality is much more than what people talk about. If you ask people what is software quality, then you get an answer like testing and bugs, or they talk about process compliance. But in my opinion, it's much, much more, and that's what I try to encapsulate in the book. And that resulted to the fact that I'm also speaking and training in software quality. And that was also the reason that when I joined ASML, I made the choice to not continue as a line manager, but to continue as a software quality manager to walk the talk. So, who knows ASML? Okay, and then the next question is, who knows the products ASML is producing? And I see less hands. ASML is created in 1984, and it was a joint venture from Philips and ASMI. And during the 40 years, we grew to Europe's biggest tech company by market cap. We have about 44,000 employees all over the world. Some people think that ASML is producing chips. And that's exactly what we are not doing. ASML is producing machines which are needed in the manufacturing of chips. And if you look to a chip, then in 1959, Fairchild Company was the first company who produced a transistor on silicon. And a transistor is a digital switch which you need to build logic, which you need to build CPUs, chips, and that kind of stuff. And the size of that one transistor was the size of a fingernail. Nowadays, on the same size, we build chips with billions of transistors. So it became smaller, smaller, smaller. And in this process, ASML is playing a crucial role. If you look to a chip is built out of layers. So all different layers. And all those different layers, they contain a structure. And as you can see on this picture, that when a chip is built, it first has to go through a process. And one of the steps of that process is called lithography. And during the lithography, there is, with light, a pattern printed on the wafer. And then the wafer will travel to a different machine, and in the different machine you have some chemical actions which are preparing the structure as it was printed on the wafer. And that has to be repeated for each and every layer in a chip. That also implies if the wafer comes back into the lithography machine for the next layer to be printed, then it is very important that the position is very, very accurate, because all those layers, if they are not positioned in the right way on top of each other, then you have a problem. And this all happens with an accuracy in the area of nanometers. So it's very, very small. As you can imagine, if you want to have billions of transistors on the size of a fingernail, you need to be very, very accurate. And that's basically what ASML is doing. Here you can see a picture of our EUV system. I'm not going to the details, but it's a huge system. And there's a lot of mechanics, a lot of electronics, and a lot of physics. And you can imagine that there's also a lot of software in this machine. We're talking about 45 million lines of code. So that's not a little stack, there's a lot of software. And all the software is needed to make sure that we are able to expose the right structures on the chips. Talking about software, you can also imagine that in such system, software quality is very important. And if I'm talking about software quality, I would like to refer to what I call the 1+3 software quality model. So you can see a quality model which consists out of 4 quality types. At the bottom, we have product quality, code quality, and design quality. At the top, we have organizational quality. Product quality is the perceived quality of the system, as perceived by the user. So how it is experienced, how well is it performing its task it's designed for. And then we have 2 types of software quality which are internally, design quality and code quality. Design quality is about the structure of the software, and code quality is about the code itself, the readability. How well is it understood by other human beings? And on top, you can see organizational quality. The definition of organizational quality is the capability of an organization to develop high-quality software. Typically, you can think about craftsmanship of your people, culture of your company, your infrastructure, tools, that kind of stuff. And you can also think about if organizational quality is not at a sufficient level, then in this model, I would like to replace the word enables by the word disables. And that's also the reason why I took organizational quality into the model of software quality, because you can argue, of course, is organizational quality part of software quality? But because it's the fundament and it's so important, I pulled it in. In 1992, Ward Cunningham started to talk about technical debt. Who's aware of technical debt? Everybody, almost. And he introduced the metaphor of technical debt to make it possible to discuss with business people about imperfections in your software. Imperfections which slow you down in your development. And slowing down is called paying an interest. It's compared to paying an interest. Next to that, you can think about solving those imperfections, refactor them, stuff like that. And you can refer to that as a repayment of your loan. Yeah, and by having that metaphor, it was possible to discuss with business people. I would like to extend technical debt into quality debt. Because if you look to the definition of technical debt, then technical debt is associated to internal software quality. And in the 1+3 software quality model, that's code quality and design quality. But we can also have debt in product quality and in organizational quality. Here you see some examples in product debt. It's about incomplete requirements, insufficient testing, or not solving bugs if they are found and let the bugs remain in the software. There are examples of product debt. Some examples of technical debt: you don't have a design, you have an inconsistency between your implemented design and code with the intended design in your UML models, or you have bad code, code which is complex and hard to understand by other human beings. Some examples for the organizational debt: it's about inexperienced team, it's a bad culture, which is an example, or bad tooling and stuff like that. If we talk about technical debt, I would like to go to some details, and we talk about complexity. Then if you look to complexity the teams are facing, then I would say there are 2 sources of complexity. The first one is external. Think about the machine we have to build at ASML. You can imagine that the complexity of building that machine is huge. That's complexity which is imposed on the team. It has to do with physics and stuff like that, and we cannot change that, but we have to solve it. And that's basically the requirements and the constraints. Next to that, the team is facing internal complexity. And the internal complexity is the complexity they built today and will face tomorrow. So that's the complexity of the software they develop and they build. The good news about the internal complexity is that we are in control of it because we create it ourselves. If you then look to complexity in software, then this is a definition from John Oosterhout. Complexity is anything related to the structure of a software system that makes it hard to understand and modify it. And that's also the reasoning that increasing complexity will slow you down. And then again, what is causing it? It's caused by dependencies and obscurity. And I would like the dependencies, then you need to think about dependencies between the different entities in your software structure. I would like to show you a picture. This picture is showing the dependency graph, and the dependency graph is showing the dependencies between the entities. It's generated out of code. And now I would like to see some hands. Who thinks this is a complex, bad design? Please show me some hands. Okay, then who thinks this is a good design? So, who didn't raise his or her hand? Most of the people. Why didn't you raise on one of the questions? Is it a mediocre design? Okay, I would like to show you a next picture. How about this one? Please show me some hands. Who thinks this is a bad design? Now I would expect all hands. This is what we call spaghetti software. Because all the dependencies, between all the dependencies, they look like a bowl of spaghetti with all the spaghetti strains all mixed through each other. And by the way, spaghetti software is not software produced by Italians, because also other people can create spaghetti software. But this is indeed, you can imagine that the complexity of this piece of software is much higher than the complexity of this piece of software. Then I would like to show you an example of some code. Is there anybody in the room who can explain me this code? Okay, normally I also show this piece of code during my presentations, and there's a room full of engineers, and I didn't get anybody yet who was able to explain me this code. This is complex code. And now imagine that your poor engineer has to modify this code. He has to make a change in the code. And then let's hope at least that there are test cases, which can be executed in regression, those test cases, to see whether he breaks something. And otherwise, this is really a bad piece of code. It's way too complex, too many nested loops, and that's quite complex. And here we have a comment in the code. Dear programmer, when I wrote this code, only God and I knew how it worked. Now only God knows it. And this is not a joke. Do we have any engineers in the room? Do you recognize it? Yes? I think most engineers do recognize that they wrote some code and they confronted with the code they wrote maybe half a year ago or maybe 2 years ago, and they don't understand anymore what they did. So it's reality. And then, of course, you have increased complexity. And that's also why, as an engineer, you always should take in mind that you have to be able to understand your code even after years. I would like to go to another example of quality debt into product debt. But what you're looking at is a graph which is created by Jones and Capers. They did research in industry. And this graph is showing 3 lines. You can see the blue line. And the blue line is showing when bugs are inserted. And basically the picture, as you can see, 85% of all the bugs are inserted during coding. We're not so very surprised about that. Then we have the orange line. And the orange line is showing when those defects were found, when they were detected by testing. And you can see that the majority of the defects were found during system test. So this is what the research of Capers and Jones showed. And then we have the red line. And the red line is showing cost associated to solve a bug in relation to when it is found and when it is solved. And as we all know, the earlier a bug is found and solved, the cheaper it is to solve it. So what you could conclude from this picture, that you would like to go to a situation in which you find bugs earlier. And we heard it already quite some time. Shift left. This is shift left in testing. Find bugs earlier, the orange line. Try to find the majority of the bugs during system testing and only find a few bugs during system tests or even release, because then they are most expensive to solve. This is an example, what the research of Capers and Jones showed, an example of product debt. Postponing testing to a later stage makes you slower, because whenever you find those bugs, you have to anyway to solve them, and then it takes you longer, and it's more expensive. If we translate that, quality debt, into speed of software development, then I would like to share this graph. We can see on the y-axis the speed, on the x-axis we can see time. And you see 3 lines, a red line, an orange line, and a green line. And the green line is an organization which is very mature, very quality-minded, which do invest in quality, build high-quality software. And by building high-quality software, they mitigate quality debt as much as possible. And by doing that, they can maintain what I call a sustainable pace of development. And then we have the red line. The red line is an organization which is immature, skipping quality activities. And because they are skipping quality activities, they're building up quality debt, and they are able to be on the short term to be fast. Because if you skip some reviewing, you skip some documentation, you skip some testing, you can be fast. Like the example we heard in the previous talk from Bart about a startup first focus on features. Yeah, basically what you're doing is building up quality debt and you're positioning yourself on the red line. That might be a solution, and that also might going well quite some time, but at a certain moment in time, the build-up and the accumulated quality debt will slow you down as expressed in this picture. So let's have a look at how it could look like. Yeah, so we have a blue line, and we have a team investing in quality, and then at a certain moment in time, they need to achieve a short-term goal, like making a deadline or something like that. They skip the quality activities, and they jump to the red line in speed. They do that for a short period in time, and then they fall back to their normal operation, but because they build up quality debt, the speed will be a little lower than expressed in the green line. What you then see on the picture is that there is an investment done. That's the second, this one is an investment in which they clean up the created quality debt. And by cleaning up that created quality debt, they move again a little bit more to the green line in speed. And what is happening during development is that these kinds of decisions are taken all over the place continuously. So every engineer is facing these kind of decisions in balancing whether to take a shortcut or not on quality. Yeah, and that's a reality, what's happening. If you look to ASML, what we are facing at ASML, I would like to put it in perspective of what we call customer risk appetite. And customer risk appetite is exactly what the word says and means. How much is the customer willing to accept risk? And if you look to this picture, then you can see at the left side, you can see pioneering technology. And there is the picture of our EUV system. That's extreme ultraviolet light, which is used to make the smallest possible transistors on chips. There's a new technology, and that technology is introduced recently, and we only shipped a few systems to the customer. But because it's a new technology, the customer is willing to accept risk. Because the customer knows what is important for the customer, that he is able to produce these most dense possible chips to produce them. And then if the quality of the system is at a lower level, he doesn't care too much. So the customer risk appetite is quite high. Then next to that, we have what we call essential technology, like our TwinScan and XT. And our TwinScan is using DUV. And DUV is deep ultraviolet light, which is already a system which is in the market for several decades. This system is used for bigger chips. Yeah, so not in a sense more transistors, but less transistors per square millimeter. And they are used in high volume production. So the risk appetite for these systems, because it's a mature technology, is much lower. Customer is not accepting a low quality because it's essential in high volume production. And then next to that, we have what we call supporting technology. And supporting technology is real-time analysis performed on the result of the chips. So like I said, a chip is built out of layers, and whenever one layer is produced, it's measured. It's measured by metrology equipment like YieldStar, and basically it's measuring how well the layers are positioned, how well the patterns are made on the chip itself. And based on the results of that measuring, data analytics are performed and corrections are calculated to be applied to the next layer in the chip. This is also part of high volume production. It runs real time during production, so also here the risk appetite is very low. So how is that related to the picture I showed with the speed? If you look to the new technology, the pioneering technology, then the innovation is important and also the innovation speed is important. And that in combination with a high customer risk appetite, the temptation to skip quality is very high. And sometimes it's also happening that we skip quality just to make the deadline, and especially in the pioneering technology. And people should realize that over time, that pioneering technology will shift to the right. So in this picture, it will shift toward the low customer risk appetite. And every shortcut you take on the left side on the short-term speed to make the deadline will slow you down for the long-term speed. So you're building up your quality debt by making those shortcuts using the customer risk appetite as a reason to do so. And then the question, of course, is how much do you want to bulldozer? So how much of the quality debt do I want to shift into the future and will be confronted with whenever my product is shifting to the low customer risk appetite? And that basically is one of the biggest challenges also ASML is facing, because we want to deliver innovation speed to our customers with our new products. But whenever those products get into production and they become part of the high volume manufacturing plants of our semiconductor companies, then of course we are facing the shortcuts we made. And then the question is indeed, how do you balance between long-term and short-term speed? So how you could do that, for instance, is at least start measuring. Try to quantify your quality debt. Yeah, for instance, by measuring it, measure your test coverage to answer the question, did I test sufficiently? And then also measure how many bugs did I found and how many bugs did I not solve. So how many open bugs do we have in the software whenever we ship our software to the customer and make that visible. You can also run static code analysis or static design analysis on your code base to get insight and on some aspects for your software quality. Next to that, I would recommend to track quality debt. Create a quality debt backlog. And a quality debt backlog can contain the stuff you measure, but it will also contain the stuff you cannot measure. And that's the input from your engineers. That's the ideas of the engineers where they indicate, here we do need to improve our code, or here do we need to improve our design. Put that in your backlog. What you then can do, if you have such a backlog, then my recommendation always is take that backlog in the context of a roadmap of your future. What I mean by that, as an example, if you have to prepare a new release, you get a list of features to be implemented in that release, then review your quality debt backlog against those features. And then the quality debt items which are significant or related to those features, select them and take them into your planning. And what I mean by that, as an example, is if you have a function in your software with a high cyclomatic complexity, if you don't need to change that software, then don't touch it. Keep it as is. But if a change in that software is needed because I have to build that feature which is on the planning of my release, then pull it in. And make sure that you refactor it to have a lower cyclomatic complexity. Thank you.
Are there any questions for Ger? You get to pick, Maxima.
Thank you. Hi, Ger. A question, like you're building equipment that has never been built before by anyone, right? So all the software that you built is one-off, right? It's the first ever being built. So if you mentioned an engineer comes up with an idea that will bring improvement to the software, do you treat it like a bug, or do you treat it as, you mentioned the backlog, but the moment software is put in the equipment and released to the field, how do you handle these type of improvements? Do you see that as a bug, or is it somewhere in the middle?
No, it's not necessarily a bug. Of course, it can be a bug. But if it is an improvement, like I would like to redesign a piece of software because it's too complex, or the example I mentioned, I have this function with a high cyclomatic complexity and I want to bring down the high cyclomatic complexity, that's not a bug. That's really what we indicate as a technical debt item or a quality debt item. So that's also a specific type which we use for identifying such a backlog. Does that answer your question?
Yeah, so it's not a negative, but it can also be a positive.
It can for sure also be positive. And I think that looking to the situation we are in and many companies are in, technical debt, quality debt is inevitable. Just accept it. Yeah? But what is not inevitable is not managing. Yeah, there's a choice whether you manage it. And your current state of the software is your starting point, so look ahead. And then if people come with issues they want to improve because it's technical debt or quality debt, then take it as an opportunity. And then also assess that opportunity, like I said, assess that opportunity against your next release to make a decision whether you should take it or not. Because also an opportunity needs to have a return of investment. Okay?
Okay, thank you. Yeah.
So I know this is not the AI section of today, and I'm not a coder, I'm not an engineer, but you did ask us if we knew what a piece of obscure software was. So I don't know this, so I took a picture with my phone and I prompted what is this in ChatGPT, and it's actually telling me what it is and what it's trying to do, and most likely that you're using it to show that this is obscure. It's telling me a couple of functions that is most likely like a C or C# syntax and whatnots, and what it makes it obscure, that some variables are cryptic and so forth. It's also asking me at the end if it would like me to simplify it or write it in Python so I can understand it and make changes. So this is what AI is doing right now. I don't understand the answer even. But I do think, and I would like your opinion on this, what the impact is on the cycle you've shown us on technical depth and gaining it, gaining the time back. Does this, in your opinion, will this, in your opinion, make it easier to decide to go for speed because technical depth can more easily be kept up with?
I think the answer is it depends. I understand what you did, and technical depth of AI might be able indeed to help in solving technical debt. But in my opinion, AI is also creating technical debt. Yeah, like we heard previously, it is important that the code generated by AI is reviewed. And then we come again to what I call clean code. Yeah, who knows the definition of clean code? Clean code is code that works and is understandable by other human beings. Code created by AI is not necessarily understandable by other human beings. So in that sense, AI can also create technical debt, and in that sense, it could also accelerate technical debt. But I'm pretty sure that if you use it in this way, like solving and understanding functions, ask for assistance, it's also helping, yes. So from that perspective, yes, I understand what you did. Okay?
One more question?
I'm just curious that you showed us the some lines, green, for the speed of the technical depth. Is the green line a perfection, or it can exist in the real world?
Sorry, I didn't understand.
There were some lines showing the graph to show us the speed and the technical depth.
Yes.
And the green line was like a steady one without any jumps. Is it a perfection, or it can be real? It can be exist in the real world?
It's a perfection. I think the green line does not exist. Yeah, so the green line would be an ideal world, and like I said, technical debt or quality debt is inevitable. So you will always have it. You should also take in mind, even technical debt can be the realization that you realize if you have built something, you realize, oh my God, now I do understand the problem, I should have done it differently. At that moment you have technical debt. Yeah, and I don't know whether you guys are familiar with Fred Brooks. He wrote a book in which he states that the software system should be built twice. The first time you build a software system to understand the problem you are solving by building it, and then you can build it in a proper way. And that's also a way of a form of technical debt, realizing, oh, I should have done it differently. So the green line is an ideal world which does not exist. You are somewhere on the orange line if you're lucky.
Thank you very much, Ger.
Thank you.